Welcome to Investigation 4.2. In this investigation, we are titling this thing Representing Exponential Decay. So we are looking at how to draw graphs or maybe look at graphs of exponential decay and then also write equations. So that'll be nice and fun. Our focus question: how can you recognize an exponential decay function from a contextual setting, table, graph, and equation that represents the function? So in other words, you're going to be looking at words that describe exponential decay, so stories and things like that, tables, graphs, and actual equations. What's cool with exponential functions, exponential growth and decay, we can do lots of real life stuff. So let's understand some of the terminology, and then we'll look at some real life scenarios. So here's some words worth knowing. I'd like you to add this to your words worth knowing section. First of all, we have exponential decay. In exponential decay, we are essentially looking at an equation or a situation that shows that we have a constant decrease in a situation. So essentially, you could be looking at medicine inside someone, nuclear waste, and thinking about how much waste there potentially is or how much nuclear radiation there potentially is and how that decreases. So it's an equation or situation where there is a constant decay of the initial amount. So I want you to think of decay being like a decaying house or a decaying log. If you look at a log that is being worn away by various outside debris, outside weather, and that sort of thing, it's slowly falling away, dying, it's smushing itself in, it's slowly becoming less and less strong. So think about decay being less and less. Decay factor, very similar to growth factors, except instead this is our constant amount that our function decreases by. So essentially, if we think about our decay our exponential growth or decay equation, we're talking about our decay factor being this b. So this b is our decay factor. So the decay factor, one thing that we need to know is it's always going to be less than 1. Okay, less than 1. So it could be 0.9, it could be 0.011. It could be tiny. It could be pretty close to 1, but it's less than 1 no matter what. As well, we have a rate of decay concept that we're going to add, and that is the same sort of concept as decay factor, but it is a percentage. And there will most likely be, when we think about decay or rate of decay, if something is decaying at a 10% rate, that means its decay factor, so we can look at the remaining amount, is going to be 0.9. So let's start already to think about how 10% and 0.9 sort of relate to each other. If you think about a percentage being, essentially, if we looked at 100%, we could rewrite that as the number 1.00. If we think about 10% rate of decay, 10% rate of decay is 0.1, so therefore we would say 1 minus 0.1 would get us that 0.9. So that's our decay factor that we would multiply over and over and over. So our rate of decay is kind of thinking a little bit opposite, and we're going to have to wrap our mind around this. So look, let's try a couple of scenarios. Here's our first real life scenario. Ooh, that was almost scary. All my stuff almost disappeared. So we have this situation where we have the following information showing a graph and a table of a particular medicine and how it breaks down in a person's system. So essentially what this person is doing, or what is happening here, is this person has popped a couple of pills, maybe ibuprofen or Tylenol. They take 600 milligrams of it, and we're seeing how that pill over time works within that person's body. And what we need to do with this is actually figure out how it breaks down and potentially what the rate of change is, or what the essential decay factor is, and that sort of thing. So let's notice a little bit about this. What I do notice is we have a decrease, and it's that sort of curve decrease that we've been seeing with exponential decay, and what we've been seeing with growth rate, or like growth, or exponential growth and that sort of thing. But what I'm seeing also is it's not happening as fast as I would anticipate. So let's find out what this actual difference that we're seeing is. So I'm going to scoot over so we can see a little bit more of what needs to be asked. And it says specifically, how does the medicine change from 1 hour to the next? So the way we can look at this is essentially looking from 600 to 450. Let's actually do a little bit of math and see what the difference between those two things are. And as you remember with finding our growth factor in previous investigations, we've taken the number that was in the second place and divided it by the one in the first place. And we can do that exact same thing here. So essentially what we're going to do is we're going to say 450 divided by 600 gets me what? So we're going to do a little bit of math. 450 divided by 600 will get me 0.75. That's a good number because I can see between 600 and 450, we're seeing a decrease, and it's not a huge decrease, but it's a decent amount of one. So now let's see if that same growth or decay factor works for the next one. So if I had 450 and I were to times it by 0.75, I should get 337.5. So I'm going to write this down. 450 times 0.75. If this all works out, I should get 337.5. And that's exactly what we get, which is kind of cool. So our change from 1 hour to the next is essentially a decay factor of 0.75. The next part, it says write an equation to model this relationship. And with exponential growth equations, we could use this equation. Y is equal to A times B to the X. And we can do the same thing with exponential decay functions. The only difference is instead of a number greater than 1 as our growth factor, we're going to have a number less than 1 as our decay factor. So we've already said that our decay factor is 0.75, and we would be doing that over and over and over again to get the next few numbers in this situation. So it has our exponent attached to it, and we also need to figure out our starting value. And our starting value, as we all know, is our y-intercept, so that means the time in this situation needs to be 0. So right when you pop those pills, how many milligrams of medicine do you have within you? And as you can see, that point in time is on there, and we have 600 milligrams. And then very last, we need to add our y. So there is our exponential decay function for this particular situation. Let's move on and let's look at one other scenario. So here's our next scenario. Many people suffer from diabetes. Some of them have to give themselves insulin injections daily to maintain proper blood sugar levels in their body. Otherwise, serious health side effects could occur, such as comas or even death. Use the table to determine the amount of insulin in a person's bloodstream if the rate of decay for insulin is 5% per minute. So it's just enough to sort of get this person stable, and perhaps after that they're going to need to eat a meal or something else. So the insulin just sort of gets their levels back on track so they can essentially function a little bit longer. So here we go. We have time in minutes, and we have 1 through 8 minutes, and we need to look at the insulin in the blood. It says in here that we have a decay or rate of decay for the insulin of 5% per minute. So if we think about what it meant for rate of decay as its definition, 5% per minute means that whenever a minute goes by, 5% of that medicine leaves my body or it has been used. The remaining 95% is still within my body and is still an active medicine. So if at 1 minute, or 0 minutes, I should say, I shouldn't even have a 1 here. I'm going to change that to 0, this to 1, this is to 2, 3, 4, 5, 6, 7. I'm glad I caught that. At 0 minutes, if we first inject ourselves with 10 units of insulin, after 1 minute, we are now no longer at that 10%, or 10 units. So let's kind of understand what's going on. Let's complete this table. If I have 10 units in my body, I need to figure out what 5% of that is. So 5% can also be written as 0.05, essentially as a decimal. And if I were to multiply those two things together, I should be able to find out what 5% of 10 is, which is 0.5. Now, if I were to not be thinking very properly, I potentially could write 0.5 in here for the amount of insulin that's in the blood. But in all reality, a decay rate is telling me how much has left my body, not the active medicine within my body. So at this point in time, that 0.5 is incorrect. I need to actually subtract 0.5 from 10. And if I do that, I end up with 9.5 units. So I still have 9.5 units of active insulin in my bloodstream, meaning that I have 9.5 units that's working still. From there, I need to figure out what 5% of 9.5 is and subtract that from 9.5. Or, get this, I could also think about this in a slightly different way. I could be careful and create an equation for this. So first of all, we know what our starting value is, what our y-intercept is. That's 10 units. So that 10 units is in our y equals a times b to the x equation. We need to figure out what our decay factor is. What would I multiply 10 by to get 9.5? So just like in our previous equation, if I were to take 9.5 and divide it by 10, what would I get? I would get, 9.5 divided by 10, I would get 0.95. So that is my decay factor. So I'm going to add that into my equation, 0.95. And how is that related to that 5%? Well, it's the opposite. So that 5% is everything leaving my body. The 0.95 is what remains in my body. So from there, I can add in a power of 2, I can add in a power of 3, 4, 5, whatever it may be, and finish this table. And so that is exactly what I'm going to do. Wait for a little bit of math magic. So now I've finished my table. I have for our final at 7 minutes, I still have 6.98 units or so of insulin left. So you can see after time, this isn't a sustainable thing for this person. They're going to need to eat a meal. They're going to need to get their blood sugar up in some other way. But it buys them a little time. It sort of gets them back on track. So as you can see, this change each time is not huge. It's not 5%. It's 0.95%. So be careful not to confuse the decay rate or the rate of decay with the decay factor. They're different things. The decay factor is just talking about what is remaining inside the body or inside of whatever, or what is remaining in the situation, and the decay rate is typically talking about how much is leaving, how much has disappeared. So they're kind of opposites. They fit together like puzzle pieces. One is opposite than the other. So you're going to have to do a little math if you're given the decay rate versus if you're given the decay factor. So keep that in mind as you move through this investigation. I hope this video helps sort of define some things in your head and work on the investigation and the homework. Enjoy!